This week, we're going to build off of the compound interest work that you did last Thursday and talk about ordinary annuities. By definition, an ordinary annuity is a sequence of equal, regular, periodic payments to be made in the future. There are lots of annuities that we see in real life. When we have an ordinary annuity, the equal payments have to be invested each payment period. In other words, you have to put money in the same number of times a year that the interest is compounding. The applications of this are retirement accounts, IRAs, 401ks and 403bs, which are other ways of doing retirement savings. And whether you have a 401k or 403b depends on what type of job you have. Loans are annuities, and mortgages. For today, we're going to focus on the savings side of this, the IRAs and 401ks and 403bs, and then tomorrow we'll look at the mortgages and loans. So when you have an annuity, you don't put all the money in at the beginning, and that's the difference between an annuity and a regular compound interest problem. So here's the example that we're going to break down quarter by quarter. You begin investing $100 a quarter into a retirement account that pays quarterly interest. If the account pays 5% APR, how much will be in the account at the end of the first year? So in this example, you work for the first quarter, and at the end of that first quarter, you put $100 into the account. And then you continue working, and at the end of the second quarter, you're going to earn interest on that $100 that was sitting there. So $100 is going to earn 1 plus its 5% APR, but since this is compounding every quarter, you would earn 1/4 of 5% for that quarter. And then also at the end of the second quarter, you would put in another $100 of your earnings. When we put this in the calculator, we see that at the end of the second quarter, you have a total of $201.25. Then at the end of the third quarter, you're going to earn interest on that $201.25. You're going to multiply that by 1 plus 1/4 of 5%. And again, you're going to deposit $100 of your income. So at the end of the third quarter, this is $303.77. Then at the end of the year, the fourth quarter, you're going to take that $303.77 and earn interest on it, 1 plus 1/4 of 5%, and add in another $100 of your earning. And at the end of the year, this account will have $407.57. Now, if you could have afforded to put $400 in an account at the beginning of the year and let it sit for the whole year, 5% of $400 is $20. So this is less than 5% of the $400 you have put in. However, what happens with an annuity is you put money in as you earn it so that you don't miss it as much. In this example, you may not have $400 to put into the account at the beginning of the year, but by doing $100 each quarter, you're spreading that out and not missing the income. There's a formula to find the future value of an ordinary annuity. Future value is how much money you have after a number of years. In this formula, we're going to use capital R for the equal payment. That's the amount that you put in each compounding period. A lot of these examples, the compounding period is monthly. Sometimes it's twice per month, but most of them are monthly, just because that's when the interest is compounding. Lowercase r is APR. Again, APR is always annual percentage rate, which always needs to be divided by the number of compounding periods, and N is the number of compounding periods per year. The formula for future value says the future value, S, is equal to the monthly, or the equal payment, or capital R, times this fraction. Now, R is not in the fraction. In the numerator, we have 1 plus the rate over N raised to the NT, that's number of compounding periods per year times number of years, minus 1, all divided by R over N. The formula is obviously more complicated because we're adding money to the account as we go through. With a regular compound interest problem, you put all the money in at the beginning and let it sit and earn interest. Here, as you are earning interest, you're also adding to the account. So here's an example. Suppose that you are going to make monthly $10 deposits into a retirement account that pays an APR of 8% compounded monthly. So the $10 deposits, that's the capital R. That's how much your equal payments are. The APR of 8% is our lowercase r. Since it's compounding monthly, N equals 12. What is the value of this account after 40 years? That's our T. So when we plug into the formula, future value is the amount you pay each time times 1 plus the rate over N raised to the N times T minus 1, all divided by R over N. I'm going to do a separate video on putting these into your calculator, but if you do have the fraction bar available in that shortcut, alpha y equals, I would definitely recommend using that for these because you want to make sure that you are putting all of this into the numerator. When you put this into the calculator, the value should be $34,910.08. With these accounts, the reason you would do this is that $10 a month is not something that you would miss as you save for your retirement. Now, this final value of $34,910 is probably not enough to retire off of, but what we also need to look at here is how much money did we actually put into the account? How much money did we put in? We put in $10 a month for 12 months a year for 40 years. So the only money that you took out of your earnings and put in the account is $4,800. We ended up with $34,910.08. So if we take our future value and subtract the amount that we deposited, what we end up with is $30,110.08 in interest. The moral of the story with these savings is the longer your money sits and earns interest, the more money you're going to earn in interest. And we can also compare what happens if we change rates, if we change the deposit amounts, and so on. So one last example. Everything is the same in this example, except we're going to double how much we're depositing each month. So now our R is $20. Our rate is 8%, and again, it's compounding monthly, so our N is 12, and it's still 40 years. So I'm going to take my future value is my monthly deposit times 1 plus our rate over 12 raised to the NT, so 12 times 40 minus 1 is in the numerator, and then the denominator is again R over T. When you put all this in your calculator, what you get is a future value of 69,820.16. You may notice that we put in twice as much each month. Our future value is twice as much. How much did we put into the account? $20 a month, 12 months a year, 40 years is $9,600. How much interest did we earn? Take the 69,820.16 and subtract the 9,600. You earned $60,220.16 in interest. By putting in twice as much each month, we've earned twice as much in interest. For the worksheet today, I want you to make sure that you are careful with how you put things into your calculator. And for each problem, you just need to write down what calculation you're doing. You're going to show everything plugged into the formula and then use the calculator to find the answer. If anyone is having any calculator issues, please let me know.